Okay, welcome back. It is now my pleasure to introduce Thorsten Joachims, who received his PhD from this very university in 2001 in the working group of Professor Katharina Mohrek. And he's now a full professor for machine learning at Cornell University, with the current research focuses on combinations of theory and system building in machine learning, with applications in information access, language technology, and recommender systems. In the past, he also worked a lot on counterfactual and causal inference, on ranking, structured output prediction, support vector machines, text classification, and more topics. Today, he'll be giving a talk about counterfactual evaluation for learning for interactive systems.
Cool, thank you.
Yeah, the floor is yours.
Yeah, so yeah, I got my PhD right here. Actually, I got all my degrees from here. So, and now I'm back for my sabbatical. So, you know, it's in German, it's, you know, you actually call your advisor, your PhD advisor, your father or your mother, your PhD advisor, or you know, your PhD mother or father. And, you know, it binds you. So you keep coming back. So you have something to look forward to. So I have a little cold. I tested 4 times over the last 3 days. It's not COVID, but I hope my voice actually makes it all the way through. So this is a shorter version of a tutorial that we gave at the last Rexus conference and at the last KDD conference. And I normally give this together with my PhD student, Yuta Saito. So a lot of the slides actually are Yuta slides. And I just wanted to acknowledge that. So counterfactual evaluation and learning for interactive systems. Probably many of you don't actually know what that means. So what I really want to do in this talk is kind of sensitize you to thinking about machine learning in a different way. That is not your standard kind of supervised learning prediction way, but to actually think about it in terms of that our systems are taking actions. They're actually like active participants, autonomous agents in the world. So this is much closer to reinforcement learning, but applied to systems that we have online, like search engines, recommender systems, which have tremendous influence on everybody's lives and on our economy. Okay, so I'll introduce this kind of intersection between recommender systems, information retrieval, machine learning, reinforcement learning. And depending on where you come from, you will know it under different names. So like in information retrieval, it will be called counterfactual evaluation and learning. In kind of recommender systems and in kind of industrial settings, they will call it like offline A/B testing, and unbiased, maybe learning to rank, off-policy evaluation or off-policy learning if you're coming from a reinforcement learning background. So it's all the same stuff, basically, more or less. And so to keep it short, I'll call OPE kind of the evaluation problem, OPL, the learning problem. And so what I want to do in terms of learning outcomes is really kind of explain what this actually means. It's a different way of thinking about machine learning, and give you the foundational concepts so that you can then afterwards go and read on your own, read the research literature, and kind of know how things fit together. 2 parts. The first part is this evaluation. It's about 40 minutes. And then we'll take a short break. Just everybody relax a little bit, get something to drink. And then the second part is going to be the learning problem. Okay, so off-policy evaluation. What is that actually? So as I said, the way we use machine learning in many applications is actually not in terms of making predictions. Truly, in some cases, we want to predict what the weather is like tomorrow, right? But very often we use machine learning to actually make decisions, to take actions, right? If you think about many of these systems here, like in newsfeed, it uses machine learning not to predict what you like. That's maybe a means to an end, but instead to like take an action and recommend that news story to you. Or a search engine, you type in a query and then it takes an action of showing a certain ranking to you. And it's an intervention in the world, right? And it could have taken many other actions. So, you know, all kinds of recommendations. And also all the way into the physical world, right? If you think about autonomous driving, right? It's not predicting, where the road is. It's about steering in the correct way to keep you on the road. So all of these systems are about making decisions and taking actions. They're not necessarily about making predictions. Predictions can be very helpful for that. But the direct thing that we want to optimize is the decisions, the quality of the decisions. So here's a very tangible example. You come to a e-commerce site, and then the system takes the action, maybe you type in a query, takes the action of showing these 3 items to you. And then what the system can measure is how you react to this action, right? Do you click on anything here, or purchase anything, or look at something for a long time, or something like whatever your metric is. So you have some request coming to the system making a set of recommendations. That's the action, and then you observe a reward, a click. And notice the goal here is to maximize the reward, right? It's not to be as accurate as possible into predicting click-throughs. So a little bit more formally, many have seen this kind of setup. It's called the contextual bandit setup. So user comes in with some context vector. Can be a query, can be your user profile, like what we've done in the past, some features describing you. Then the system is a policy. It takes an action. It takes this input, this context, and then takes an action based on that, like making a specific recommendation, and then you observe reward. That's this contextual bandit loop that we typically think about. And it's a reasonably good model for a lot of these interactions that we have. Basically, any interaction that doesn't have a state attached to it. So for example, if you want to predict what goes into this top banner here, like the big top position on the Netflix homepage, user comes in, maybe with some features, the time of day, day of the week, the user profile. System takes an action, puts this particular movie there, Homeland, or it's a TV series, I guess, right? And then it can observe whether you click on it, or whether you watch it to the end, or whether you watch it all within 24 hours, right? All the episodes. So it's a certain reward that kind of supposedly indicates how much you like that recommendation or that action, more generally. Or maybe YouTube recommendations. You have the query of policy evaluation. Knows a little something about you. It takes and you're now at this of policy evaluation slide deck or talk. And then there's a ranking to the right of what else you may be interested in, right? And again, that ranking is an action that the system took, and the system can then observe whether you click on something there. And you can even look forward, whether you kind of engage downstream. Again, this contextual bandit loop. And finally, again, this product recommendation, there's a context. The action is this set of recommended items, and the reward is whether you purchase something or click on something. Does it make sense? Any questions throughout? Just raise your hand or shout out. I'm happy to take questions. All right, and there's many more, like news recommendation, music, podcast recommendation, like personalizing the artwork. That's something that streaming services do, right? They try to find the right artwork for the movie that highlights what you may be interested in this movie, right? All kinds of ad problems, and also like medical decision problems, or how do you personalize education? Many of those fall into this kind of contextual bandit thing. So it's very practically relevant, and there's a lot of attention from industry. So, okay, so I'll talk about 2 problems here. The first one is policy evaluation, and that means you have a policy, like some function that produces rankings or some function that makes recommendations. You want to evaluate how good it is. What is its reward? An expectation, let's say. That's the policy evaluation problem. The second problem is the learning problem. Now we have a whole bunch of policies, and you want to pick the best one. just like you typically have in a kind of supervised learning problem. So let's start again, policy evaluation, because once we know how to evaluate, we can certainly also do learning, right? We can just try all of these policies and evaluate them and pick the best one. Okay, so I've used this word policy over and over again without defining it. So let me actually really explain what a policy is. So a deterministic policy is just so you typically call it pi. It's just a function that takes in a context X and outputs, this is the action you should take, A. And so it's a mapping. It's a deterministic function from context to action. And I've depicted this here. For a particular context X, this box is the space of all possible actions. Let's say actions are continuous. So every point in this space is a different action that the system could take. And policy pi1 takes this kind of reddish action, and policy pi2 takes the greenish action. And red and green is supposed to indicate the reward. So red being bad, reward, negative reward or zero reward, and green being good, positive reward. So two different policies take two different actions that have two different rewards, right? And ideally, we want to reliably pick green actions. We want a policy that always picks green actions, or as green as possible. Now, we typically don't think about policies as deterministic functions. And it will become clear throughout the tutorial why it's actually much more convenient to think about them in a stochastic way. So instead of having a deterministic function, we think we have a probability distribution, a conditional one. Given a context X, pick the actions from some distribution. And that's our pi, our policy. And so here, that's these kind of shaded areas, right, that kind of indicate, oh, with high probability, you pick something from the darker areas and lower probability from somewhere else. And of course, stochastic or the deterministic policy is just a special case of the stochastic policy. Let's put all the probability mass in one point. All right. So there's a very natural probabilistic interpretation now that we have. Contexts come in from the outside world, from this distribution P of X. We don't know what P of X is, but we assume that they come in IID, right? This is like users coming to your system. For every X that comes in, our policy now samples stochastically an action to take. And then for that action and that context, it gets some noisy reward, right? That's this probability distribution P of R given X and A. And so now just by running the system and fielding the policy and executing the policy, we collect data that is triples of context, action, and reward. And we have, if you're running a search engine, if you're running a recommender system, you have millions or billions of these, right? A lot of data like that. And to some extent, it's very valuable data because it directly indicates what your users or customers were actually interested in, right? How did they react? To some first approximation, the rewards are probably very meaningful. So we actually know now the overall distribution of our data. So it's just this big product over a whole data set because the contexts are IID. And what we control is the policy. What we don't know is the reward distribution and the context distribution. But we can sample from it by fielding the policy. And that's how we get our data. So now, what's our goal? As I said before, we want to optimize the decisions, right? We want to make good decisions. And the way that we say this, or that we express this, is to the value of a policy, which is just the expected reward that we would get by executing the policy on these contexts that are coming in. So it's just this big expectation where we take the expectation over the context, over the actions of our policy, and over the rewards, how we observe them. They're noisy, right? People don't click deterministically. And so then we just take the expectation over that. So like a particular policy, like for the context I would pick from this distribution, and for all of these contexts from that distribution, and it's just a big average over everything, right? Makes sense? Questions about this? Yeah.
Yeah, actually, I have a question. there's also another kind of research on when you're doing, for example, when you want to, for example, predict which is actually going to be the product that you want to provide the user. And usually in that scenario, you are collecting a set of queries before actually providing results, and you're providing a sort of alignment among all the possible queries that the user provided before clicking on the object and basketing. So, and here you are actually stating that you can also use this kind of reward expectation policy, but as far as I'm concerned, the reward is just provided for each action that the user is actually providing. So, but nevertheless, even in reinforcement learning, you can also have what is called episodic learning. So you're checking the whole episode, and then afterwards you're providing the reward. So this approach could also is there a way also to map then this kind of approach that you're proposing, exploiting reinforcement learning for recommendation systems, also for forecasting actually the whole set of actions before deciding the reward?
There's a couple of simplifications that I'm going to make here, because that gives you because then you can have very nice algorithms and very efficient algorithms. And one simplification is that, you know, you can, if you have some episodic kind of system, right, and you have maybe a combinatorial space of actions that are getting executed during that, you would treat this as a single action here, as some atomic action. And then again, it becomes, you know, here's a context, here's a set of or string of actions that I took, and here's the reward. Doesn't scale particularly well when you do that. And you would have to come up with some compact representation. In principle, you could. Otherwise, I think what we'll talk about in terms of learning problem actually matches what you're thinking about, right? So far, I've just kind of described where does my data come from. You know, the data comes from this operational system. There was some policy running on the system that collected the data. It took certain actions, didn't take other actions, right? And for the actions that the system took, there I will observe the reward. And later we'll use this data to then do learning and try to maybe optimize for a particular, you know, optimize the policy to be particularly good at maximizing reward. Yeah. Okay. So this is our goal. We want to maximize expected reward. So the standard way of doing this is through an A/B test. So here's what you can do. You have some policy pi e that you want to evaluate. You want to know how good is this policy. So what you can do, you can implement this policy, deploy it on your system, and just, you know, serve the actions of that policy, and maybe have two different conditions. You know, 50% of the users get like the old policy, 50% get the new policy. And then you just record the rewards that you're getting, and just doing a simple average, you know, just averaging the rewards gives you an unbiased estimate of the value of the policy, right? It's the expected reward. So it's very simple. Well, conceptually, it's very simple. You actually have to do this in a big system. It's actually pretty hard, right? You have to, you know, there are a couple of things that you need to do. So pro is conceptually very straightforward. It's unbiased. If you run it long enough, you will, you know, the longer you run it with the better precision, you will be able to estimate the expected reward, how good this policy really is, right? So it's consistent and has small variance. Really doesn't make a lot of assumptions. But there's a couple of big downsides here. The first is, if your policy, new policy that you want to evaluate is bad, now you're serving bad results for a week. And that's not good, right? So there's a risk of deploying something bad. It's actually, you know, like thinking something up and coding something, you know, quickly in a notebook is one thing, but actually building something so that it robustly fulfills the latency requirements, the robustness requirements of an operational system, that's a couple of weeks of work, right? Or a month actually of work. So that takes time. So that makes it the whole process slow, and you can't really, you can evaluate maybe one policy a week or 2 policies a week, but you can't evaluate 1 million policies a week, right? So kind of this is kind of the online way of evaluating policies. You know, you field policy pi 1, you draw data from this policy, like we put it into your system, you estimate the reward. Then you policy pi 2, and you do this sequentially, right? Maybe some of this you can do in parallel, but it takes a long time, right? And every time you throw away the data that you've previously gathered, right? The data that you've gathered from evaluating policy D1, you're no longer using to evaluate policy D2, policy 2 anymore, right? That seems wasteful. You're always collecting new data and then we're throwing it away. So the key point here of this counterfactual evaluation is to only collect data once and then go through these counterfactual estimates saying that, you know, the data was collected from policy pi now, and I maybe designed this policy in a particular way. But now I want to go through the counterfactuals. I want to estimate how well would I have done? What would have been the expected reward if I didn't use pi null, but pi 1 over the last month, or pi 2 over the last month, or pi 3 over the last month? And so I collect data once, and then I go through this what if, through this counterfactual statements. You know, how well would I have done if I had used a different policy? And that's this counterfactual policy evaluation. It's like running an A/B test, but doing it offline, right? You're not going out and getting new data. You're just reusing your old data, and you still want to get unbiased estimates that are accurate. So that's the main goal of off-policy evaluation, and that's the challenge. So yes, that's just what I said, right? The true value of a policy, you want to get an estimator V hat that evaluates a new policy pi e with data that was logged from a different policy pi now. And you could do that very quickly, right? You can code up all of these new policies, and you can go through literally millions without much delay. It's only the computational cost that you still have. You don't have to go out and implement anything or collect new data. And ideally, there's no online-offline gap. What you estimate offline from this data is the same as what you do online. Great. The pro would be, it would be very scalable. No harm due to bad policies, right? The policy, if you have a policy that we want to evaluate offline, well, we never put it in front of actual users, right? So there's no harm done. Any cost that comes from collecting data from pi null, that logging policy, gets amortized over all the different evaluations that I'm going to do. And there's no need to productionize anything. So you can really do this very fast. The con is, and that's why people are very interested in that. The con is that it might be less accurate, and you have to make some assumptions, and you have to be careful in when this is accurate and how you set this up. And that's what this is really about. And then once you know how to evaluate policies, then you can just do learning as well, right? Then you can do just empirical risk minimization. You have an estimator, and then you can just go through your policy space. You have a space of policies, maybe all deep networks that parameterize some policy. And you can search for the one that optimizes the training reward, right? So then you can do actual batch learning with this type of data. And that's then the second half. Moreover, what you can really do with that is you can have these kind of supervised learning workflows. You can do off-policy training. You can hold back some evaluation data, some validation set, on which you can do parameter tuning. You know, you can evaluate these policies on a validation set. And you can iterate as long as you need to. And only once you're happy here, you go into an online E/B test, maybe as a sanity check, right? But if you've done everything right, then there's going to be no surprise, right? What you've estimated offline will be exactly the same as what you get online. That's the big vision. Questions about this? Mm-hmm.
It's about the data collection. So if the data is biased when we do the offline, so then policy and applying that policy.
Right. So the key point is exactly right. We have to be careful about the biases that are in the data. And the biggest source of bias is ourselves, is us, right? Because, you know, whatever the policy null does, that's where we're kind of getting data, right? And that really biases, you know, what we can learn from it. And so we really have to be careful about is exactly kind of taking care of these biases in a principled way. So that's exactly what we're going to do. The way that we'll typically, so we'll design estimators now. And ideally, they give us, the goal is to get an estimate of the true value V of a policy, but just using this data from this existing logging policy. And we'll evaluate by mean squared error, just very standard. And when you have a mean squared error, you can always do a bias variance decomposition, right? That bias is whether you're systematically kind of wrong, right, off in your estimate. And an unbiased estimator would, like in expectation, overdraws of the D null of the data set be spot on. And then you have variance, right? How much this varies around this kind of mean of the estimator. So just like in standard bias variance decomposition. So, but it's very helpful to think about bias variance in, you know, thinking about what these estimators do. Okay, so there's 3 classes of estimators. There's model-based estimators. That's where we're going to start with model-free estimators. And then you can mix these 2 up. And I'll not talk in depth about the mixing the 2 up. I just want to explain these first 2 classes because they're really very fundamental. If you understand those, you can kind of get what these other things are, no problem. Okay, so how can we understand these biases? How can we actually deal with actually the missingness of our data? So let's forget what, you know, forget online systems and recommendations and ranking. That's actually, you know, if you think about it, it's actually not that different from like what a medical doctor would do. So, you know, medical doctors also prescribe treatments, and then they see the outcome for that treatment. But they don't get to see what would have happened if they had given some other treatment to that patient, right? So I know nothing about medicine. So this is my mocked up example of, you know, how to treat a heart attack. Don't take any medical advice from this. So let's say there's 3 treatments. There's bypass, you can do stents, or you can just do drugs. And so here is you can think about it as a controlled randomized trial where doctors have decided, according to some policy null, that, oh, patient X1 should get the bypass surgery. And now they observe the outcome. You know, let's say that's the 5-year survival. And unfortunately, that didn't play out well for patient X1. So for X2, they decided to do the stent surgery. And 5 years later, that person is still well. For X3, they decided to give the drugs. And, you know, 5 years later, that patient is still well. So the important thing is here that this is very similar to what we would do like in many of our online systems. So maybe you have the decision to make, there's a news box here. And should you put it in position 1 between the first and the second result, in position 2 between the second and the third, or in position 3? These are the 3 treatments that you can give. And then what you can observe whether the user interacts anywhere on that page, right? And that's what you want to optimize. So structurally, the 2 problems are identical. And so what's the difficult part here? The difficult part is that I only observe the factual outcome. I only observe the reward for the action that I've actually taken in the past. I do not see the counterfactual outcomes, all the other actions that I could have taken. And now if I want to evaluate a different policy, That means there's a policy that takes different actions, right? It would have maybe done position 2 for this problem. I'm missing the data, right? What am I supposed to do? And so, as you pointed out, there's biases that we have introduced, right? So like for this particular user, we've picked position 1. And that was not completely at random, right? Maybe it was actually, that was a user that, really likes news or so, right? And so there's lots of confounding happen here potentially, right? And I have to now think about, how do I fill in like the missing data if I want to evaluate a new policy? So the first thought that you have is probably, well, we know how to do supervised learning and prediction. Let's just impute. And that's what model-based off-policy evaluation is. So let's say we kind of come up with an imputation model that would, the black, that's the true, what the action that I've actually chosen, and we observe the true reward. And the red ones, there I impute what I think is the expected reward of the action if I took that one. And now evaluating a different policy is super easy, right? I just, go through it and see this policy pi e, what's the probability of taking each action? I take the expectation over these predicted rewards, I'm done, right? And that leaves the question of, okay, how do I come up with the imputations, right? And then I have to fill in these red values. In principle, that's not so hard either, right? That's just a regression problem. I can just take all of these black values that I had and then train a regression model that predicts the remaining values. So the black are the training data, the red are the test data, so to speak, and I just train on the black and I test on the red. I can use almost any supervised machine learning algorithms for this, right? So in principle, that works. But in practice, it often doesn't. Anybody kind of have a guess for why this can go wrong?
Data, so the regression model is not able to capture these stars. It doesn't have to see this one.
Yeah, I mean, we're dealing with a covariate shift, right? So we had a policy that picked these black values. And now our training data is whatever that policy does in terms of black values. But then our test data comes from a different distribution. And that's always tricky, right? It's, covariate shift is typically the name that people use. And if I depict it here, so let's say we have 2 features in our regression problem, and then, our, training observations are these red points and these green points. They all lie in some region of the space, right? Because that's what my logging policy kind of did. If I now want to evaluate something that's different from that, I really have to trust that my model extrapolates well. And if my model extrapolates this way, or my model extrapolates that way, makes a huge difference. So I'm really, really relying on my modeling assumptions, right? And often you do some kind of assumption that, data is linear or something like that, or is very smooth. If you happen to extrapolate well, all's good. But if not, it's often really even hard to detect that you're way off. Because you have a bias in your data, and bias are difficult to estimate. So, okay, can we avoid this? Can we avoid these strong modeling assumptions? And one way is to actually not impute these values at all, but to rely that there was some randomness that our logging policy had when it collected the data. And when we have randomness, so that it actually picked not deterministically this action, but stochastically, we can use inverse propensity score weighting. And what inverse propensity score weighting is, you know, if you're directly estimating, you know, let's say pi null's value, if you have data from pi null, then that importance weight term here evaluates to, that's a ratio of the two probabilities of the chosen action under the logging policy and under the policy that we want to evaluate. Like in an online setting, that evaluates to 1. It's the same number, both the numerator and the denominator. If we have some mismatch between the logging policy pi null and the evaluation policy that we want to evaluate, then what we do is we upweight and downweight the observations. So can depict this in the following way. Here, this is kind of, if you do on policy. And off policy, what we would do is we would upweight these observations that have large probability under the evaluation policy that you want to evaluate and small under the logging policy, and vice versa, right? That's what this inverse propensity score weighting does. It's just the ratio of these probabilities. And, you know, there's just a 3-line proof that tells you that under, it's called the full support condition, and I'll explain what that means in a second, this is actually unbiased. It gives you in expectation the right value. And you don't have to make any extrapolation. You don't have to predict. You don't have to impute. Okay, so why does that work? So up here is the inverse propensity score estimator again. So it's the probability ratio up there, right? And so remember, our policies are just probability distributions. This is the logging policy here. And let's say for patient 1 or for example 1, it has the probability 0.3 of picking position 1, picking that treatment. Probability 0.6 picking position 2 as the treatment, and 0.1 position 3 as the treatment. And now during data collection, it flips a coin and picks according to these probabilities which actions to take. And then, and in this case, it picked position 1, and we see the outcome. Our evaluation policy has different probability distribution. So it actually picks position 1 with 0.6. So what this IPS weighting does is, because 0.6 is twice 0.3, if you look at that probability ratio, it's 0.6 divided by 0.3, that's a factor of 2. So it double counts. It counts by a weight of 2, that observation, right? And so that kind of gives you, oh, yeah. Now, you know, this policy would have picked, the new policy would have picked it twice as often as the old policy. So if I multiply it with a factor of 2, in expectation, I get the right thing, right? And for the second line as well. So there it's the other way around. Position 2 was chosen, had a probability of 0.4. Under the new policy that we want to evaluate, it's only half that. So we downweight that by a factor of 0.5. And by doing this weighting, we get the right, you know, we're just kind of upweighting and downweighting the right way. And we get something that's unbiased. It's the correct value in expectation. It's like a really old trick from, you know, it comes up in causal inference, comes up in design of like survey design in many different places. So, so the important, that's what I said. The full support assumption is that this only works if the logging policy had non-zero probability of picking any of the actions. Right? This way, we don't have any blind spots. Anything can happen. If we have zeros there, then we potentially get some bias, and there's more work that you need to do to account for these biases. But if we have this full support, that any action that's chosen under the target policy has non-zero probability under the logging policy, we are unbiased. Problem is we often have high variance. So we're correct in expectation, but the variance can be large because these weights can also be large, right? If the probabilities are far apart, there could be a large kind of weight that we're attaching. You know, if you're curious, this is the proof that it's unbiased. So how do these two estimators now perform? So there's the direct model estimator. That's the model-based one, the regression imputation one. If you increase the amount of training, the amount of data that you have to do the evaluation, and this is how accurate this mean square error. So lower is better. So the blue line, the regression imputation direct model, that is better for very low amounts of data that you have. But it's not consistent. It doesn't go down to zero, right? It asymptotes because it has a bias. The IPS estimator, that has, if you have very little data, you have a high variance. But if you get more and more data, that variance goes down, right? Variance always goes down if you have more data. And eventually that actually converges to zero. So these two estimators have two different properties. One is high bias, low variance, and the other one is zero bias and higher variance. So, and those are like the building blocks of basically everything in this field of estimator design. And now there's hundreds of papers that now go into how do you actually now mitigate the variance of the IPS estimator. And there's like clipping and there's self-normalization. There's a ton of different techniques that you can use. Or how do you make the model-based estimator less susceptible to bias? And again, there's lots of papers like that. I don't want to go into depth here in this tutorial. But as I said, there's a longer version of this tutorial that now has a whole kind of section on how to design these more advanced estimators that if you want to really dive into this would be a good next step. And with that, let's take a little break. And then after the break, we'll start with how do we take these estimators now and design learning algorithms that automatically find us, not just evaluate a single policy, but find us the best policy in some policy space. All right, let's see. Okay, so this is our bandit feedback, contextual bandit feedback, right? Just as a reminder. Okay, evaluation, we know now how to do, or at least we know there are two types of estimators and what their pros and cons are. But now the learning problem is that we want to not just evaluate this one fixed policy that I came up with somehow. We want to find the best policy that is ideally a lot better than that policy that collected the data, that pi null. And we don't want to do online learning, right? We don't want to go out again and collect new data and interact with the user. There's a whole bunch of risks and issues with that. So if you think about like the big picture of machine learning, where does this learning problem fit? This is batch learning from partial information or bandit feedback, right? And so if you think about machine learning as there's online learning, where you interact with the world, right? And you adapt the hypothesis all the time. Like for the full information case, like classification or regression, there's a ton of algorithms, right? Perceptron, Winnow, the classics, right? If you have bandit learning, online bandit learning, also a ton of algorithms. It's EXP3, UCB1, depending on the setting that you have, right? For batch learning, if we have like fully annotated data, like full information data, somebody tells us this is the correct label for this classification, right? There's a ton of algorithms for that, right? SVMs, random forests, all kinds of deep networks, right? But we don't have that, right? Nobody tells us what the correct action to do, what the best action is. We just get to see what was the reward under the action that was chosen by our potentially somewhat crummy logging policy. And so what we're doing is in that quadrant, right? You want to do batch learning from partial information or bandit feedback. And so that's very close to what, that's close to an RL, reinforcement learning problem. But the main difference here is that we're ignoring state, which gives us algorithms that are much more tractable and efficient. Okay. So what's our goal? We have our data. We have a hypothesis space or a policy space of potential policies that we want to consider. Maybe, deep networks that we turn into policies or something like that. That's our space. And the goal is that we find a policy that has maximum expected reward, has the maximal value. And we want to, so that, you know, this maximum expected reward, that's typically called an online metric, right? This is what you would see if you actually deploy this policy on the system. But we want to do this learning without actually deploying anything, just with the data that we already have. So that what we're doing now is we're optimizing this online metric, but we're doing it offline. Okay, so goal we've done. Let's talk about the two approaches. There's again a model-based approach, and then there's a model-free approach. Let's start with the model-based one. And again, you can probably guess how this is going to go, right? So what we can do is just like we use our technique from the first half, and we train a reward predictor. So these were the chosen actions here. So each user is a row here. These are the chosen actions, and this is the reward that we've gotten for each of these chosen actions. And now we can train a model that says, you know, a predictor, R hat, so predicted reward for a particular context and a particular action. It's just a regression problem. And now when we have some test users, what we can do is we can simply impute all of the values, right? We can use our regression model that we've trained and predict, oh yeah, no, for this first test user, action 1 has a reward of 2, action 2 has a reward of 1, and action 3 has a reward of 0. And how do we read off a policy now? Well, we just pick the action that has the largest predicted reward, right? Very simple. So we take a regression model, predict the rewards of all the actions, pick the action that has the largest predicted reward. So yeah, that's the action with the largest predicted reward. So this is how we turn a predictor into a policy in a model-based way. Okay, so let's try this out. This is a little toy synthetic setup that actually my student Adit set up. And so contexts come in. It's synthetic. It's like here we just made up some features. And the goal is to pick for these 3 spots here, 3 out of 7 potential news articles. So it's a very simple toy problem. We see the reward. So once we kind of put articles there, we see the reward, and it's a complicated function of the articles and the context. So it's not just a simple linear function or something like that. It's something really complicated, difficult to model. And now we have a logging policy that kind of tries out in some, you know, somewhat probabilistic way, putting different articles into these different news boxes, and it makes sure that every possible combination has some non-zero probability. So we have full support. Okay, then you collect data from that, you train a regression model, you pick the action that has the highest predicted reward. And so here in this particular, it was kind of try different regression methods, and we picked the best one via cross-validation. And so this is now the true value of this policy that we derived in this way. So our production policy that we had before, and that we then, that we already had, has a value of 224. So the higher, the better. The policy that we use for logging, so we introduced this little bit of randomization to make sure that, you know, we actually try everything. That has a value that's slightly lower, so we kind of lose 10 points. And then if we then train the reward predictor and derive and field that new policy, we get something that's actually a lot worse. That's not nice, right? So we want to be at least as good as the logging policy. Here we've learned actually something that's worse. Doesn't always happen. But what happened here? And it's again that problem that we had last time, right? Like that we also had in the first half of the talk. So we came up with this regression model. We came up with some features for it. And then we had data for it, right? Those were the actions of the logging policy and the rewards that we had. Those are the red and the green points, good and bad actions. And then we trained this model. And our model now classifies every possible action, every point in this space. And now if we ask, oh, what's the best action to take? Well, the best action to take is that thing down in the corner there, which we don't have a lot of evidence for, right? It's pretty far away from where we have data. And it really depends on how our model extrapolated, right? And here, because it was a complicated underlying function, our model actually extrapolated in a bad way. And it picked these actions that were very far away and that were actually not very good. So, and it's hard to detect that. So we had model misspecification. That's basically what the problem is. And so we get a biased and not consistent learning process. But if you think about it, why do we actually want to do, I mean, do we really have to do reward regression? In a way, if we can do good prediction of all the rewards, that's great, right? If we can do that, we can read off the optimal policy, no problem. But it's actually a harder problem than just learning a policy directly, right? And so, you know, Wapnick, one of the fathers of statistical learning theory, said, you know, if you want to solve a problem, don't solve a harder problem first. And that's kind of what we're doing here, right? Because if we have the rewards, we can read off the optimal policy. But the optimal policy is actually a simpler function than, you know, than the predicted rewards. We just need to pick the right action. We don't actually need to cardinally predict what the value of that action is, right? So can we maybe avoid this kind of model misspecification problem and maybe directly learn policies? That's the model-free approach, right? We don't actually model the world, right? We don't model the reward function, but we directly want to learn a policy. So how can we do that? Well, it's actually also pretty straightforward. We can do empirical risk minimization, right? We optimize training error. Either we maximize training reward or minimize training loss. I think my slides are a little bit all over in terms of whether we're maximizing reward or minimizing loss, but it's the same thing, right? So here we are maximizing reward. And so what we can just do is we have these, like the IPS estimator from the first half. It's an unbiased estimate of our training set performance, so to speak, just like what we have in supervised learning. So we want to maximize that on the training data minus some regularization, right? We always need some regularization to keep us from overfitting. So now that's the basic schema. Now the key questions that we have, okay, which estimator do we pick? What regularizer to use? Do we use stochastic or deterministic policies? And that has a big influence on how easy it is to solve this argmax problem and our ability to use things like stochastic gradient. And once we make these choices, we basically have a learning method. So one clever reduction that you can do is you can actually reduce this to weighted multi-class classification. So here's again the IPS estimator. And if we pick a deterministic, the class of policies to be deterministic functions, so that's this I here, then if you take the IPS estimator and you just kind of rewrite it very syntactically, what you get is it's actually multi-class classification. So we want to predict the action that the logging policy took, weighted by the reward divided by the propensity. So the probability of taking this action under the logging policy. And if you find the policy that maximizes that, that's like optimizing the IPS estimate, right? Finding the policy in the policy space that optimizes IPS on the training data. So and now we can use any weighted multi-class classification problem algorithm. So it's just the weights are the reward divided by the propensity. And then whatever that algorithm optimizes is the expected reward. And that's implemented, for example, in Warple Rabbit, in the Open Bandit pipeline. And so here, just to summarize, so what is our estimator? Let's say we use W robust or IPS. W robust we haven't really talked about. It's just a more sophisticated way of doing the weighting or this combination. What regularizer, whatever your underlying learning algorithm needs. We're learning a deterministic policy, and how to solve the argmax, you just use whatever is implemented, whatever algorithm, multi-class, weighted multi-class classification algorithm you have. So let's try that out on our toy problem, like with the 3 slots. And here, this is the VW package using the multi-class filter tree weighted multiplication algorithm. It's using the doubly robust estimator. And it's picked these parameters through cross-validation on the validation set. So the production rate, ranker again, 224, 214, the long policy. The reward predictor from last time, 175. This gets a little bit better, but it's still worse than the logging policy. So this is a little disappointing, right? And it doesn't have to happen. Sometimes this works great. But what happened here? So there is a tricky issue. So let's look at what happens if you optimize, if you pick the policy that maximizes the IPS estimator. So that's the IPS estimator. Now I'm minimizing. It's a loss now, but same thing. So I'm going kind of conceptually, I'm going through all my policies. Like there's policy pi 1 in H. I'm evaluating that one, and I get a value for it. There's policy pi 2 in H. I'm evaluating that one, get a value for it, right? And I go through all of my policies like that, at least conceptually. Now, what happens? So for policy pi 1, that's maybe pretty close to the logging policy. I upweight some of the points, I downweight some of the points, but it's still an average over a lot of points. But in my big hypothesis space of policies, there is this policy pi 237 that picks actions from way up in this corner. Way up in this corner, I only have one observation from the logging policy. And what happens is it now gets a huge weight. So that weight makes it unbiased. But my estimate is now like basically unbiased, but only a single observation, right? So it has a really big variance. So the complicated part is that you just don't have in supervised learning is that if you do this minimization, there are some policies where your estimator has low variance and some policies where your estimator has large variance. And so for these large variance policies, it's very easy to overfit, right? And it may just pick something up there in the corner based on basically no evidence. So you have to account for that, right? You have to account for the fact that unlike in supervised learning, like classification, if you try different hypotheses in empirical risk minimization, the variance can be very different. So if you actually try to derive generalization error bounds for this case, and you want them to be like suitably tight, you actually get an additional term in them. So you may have seen these kind of statistical learning theory bounds, uniform convergence type bounds, which say the true value of the policy, if I optimize over some policy space, is less or equal than what I get on the training set that's potentially overfit. And then some capacity control that models the overfitting just by trying different, the number of different hypotheses that we've tried. But then this middle term then accounts for the fact that different policies have different variance. And so you get this kind of additional variance control term in there that you also need to account for. Now, these generalization error bounds are never particularly tight, but they're typically very useful in telling you what you should design into your learning algorithm. So in particular, what this says is what you really want to optimize in your learning algorithm is the performance on the training set, your estimator, the hat, but then regularize it by keeping the variance of this estimate small. So there's a penalty and there's a parameter lambda 1 penalizing the variance of this estimate, which you can use the empirical variance here, which you can estimate, plus a capacity control term, maybe L2 regularization or something like that. So you get two regularization terms. There are two things that you need to regularize for. So, and what we've done before, we've kind of dropped this middle term, right? And that's why things went wrong. So then the last thing that we really just need to pick is what's our hypothesis space. And here for simplicity, let's use something that looks a lot like a conditional random field or structural SVM, right? You're learning a weight vector W over some joint feature map. But you will see in a second that you can do this with a deep network as well. So you're learning these Ws, and what comes out is a stochastic policy that just picks from this distribution, right? It's a softmax, basically. That's all that this is. Okay, so if you put everything together, you get the POEM learning method, policy optimizer for exponential models. And what you optimize now is estimator of the risk, a variance term that you want to keep the variance small, and a capacity control term that's just L2 in this case. So this is just a summary of what this is. And so this is trying this out on 4 benchmark data sets that these are classification data sets, but we turned them into a multi-label classification data set, but we turned them into, we did like a batch to bandit conversion. We kind of simulate bandit data for this. So then there's the straightforward IPS, and then there's POEM with the regularization. And on these data sets, actually the IPS works reasonably, so lower is better here. IPS actually, in all cases, does beat the logging policy. So as I said before, that one example was kind of constructed where it failed. But if you do the variance regularization, you get another pretty substantial boost, right? So you avoid these cases where it picks a hypothesis based on very little evidence, or it picks a policy based on very little evidence. So, okay. We've discovered one way of kind of avoiding overfitting. There is yet another way of how we can overfit in this setting. That's also novel, and that you also don't have in supervised learning. And that's called propensity overfitting. So what else can go wrong? So here's a little, again, a very little toy problem. And so the rows are, again, like examples. The columns are actions. And green are good actions, and red are bad actions, bad rewards, right? And these blue boxes, those are the actions chosen by my logging policy. So now, if I ask you to find me a policy that minimizes that IPS estimate, can you tell me a policy that actually has 0 value for that IPS estimate, which is the best that you can get, right, in this set? So it has to be a policy that picks an action in every row, right? Which policies give me a 0 in terms of that sum of IPS terms? Actually, a ton of them, right? So one policy that gives me a 0 is certainly the policy that picks all the green fields. Super, right? That would be great. But actually, another policy that gives me a complete zero is the policy that just picks the first action all the way through, right? It was never chosen by the logging policy. So I never get penalized for any kind of losses there. So I can just avoid the data that I have, and I get a zero estimate based on IPS. Or I can pick something like that, right? That is also a policy that basically avoids most of the training data that I have. Mm-hmm.
Can you elaborate again what the propensity is representing here?
So that would be the probability that this action was chosen under the logging policy.
Okay.
And that's, I haven't actually specified what it is here, but maybe the logging policy just uniformly picked things or whatever it is, right? But whatever the propensities are, just avoiding the data actually gets you the best possible training performance that you could get in terms of this estimator, which is clearly not what we want, right? We don't want to avoid all of the data. So that's another way of how we can kind of overfit. And the problem is that we have two random variables, right? Normally in supervised learning, we have like our losses, that's a random variable, and we can observe, we can kind of overfit that random variable. And here we also have the actions that the logging policy took. And we can kind of weasel ourselves out of that random variable as well, and we can overfit that as well. So, how are we going to deal with that? Fortunately, this one is easy to detect. Normally, overfitting is harder to detect, but here there is a very easy diagnostic that you can do. So up on the left, that's the IPS estimate with the reward at the end. On the right, this S term, that's what we call a control variate. And I've just replaced the reward with the constant 1. So it's basically, this is estimating the value 1 in a very complicated way. But we actually know here, right, this is just a one-liner, that S hat has to be 1 in expectation, right? It's just a fancy way of estimating 1. If we see that we pick a policy and this value isn't anywhere close to 1, something's wrong, right? And in particular, if our policy kind of weasels out of all of this data, that value of S is not going to be anywhere close to 1. It's also going to be 0, just like the IPS estimate, right, of the rewards. And so a very effective estimator is that you just divide the reward estimator, the IPS estimate, with the control variate. If everything's fine, that control variate is 1, doesn't change anything, right? But if you're weaseling out of your data, then this control variate S is going to be much less than 1, and it's going to penalize that, right? So it's going to penalize all of these kind of policies that are trying to avoid the data. And that's called the SNPs estimator, or the self-normalized estimator. It has some interesting properties, also gives you a variance reduction, and is also consistent. So what this means is, well, we just plug in that other estimator into our training objective. You have the self-normalized risk estimator, so the SNPs, its variance, and then capacity control. And if you do that as well, so you get, that was the logging policy. That's if you don't do the SNPs estimator, just the IPS estimator, and then SNPs POEM, you get another nice boost in terms of performance, right? Because you can't weasel out of, out of the data anymore. And down here is the control variate. And what you can see is that, if you don't actually do the SNPs optimization, that control variate can be really far from 1. Once you do the self-normalization, it's kind of close to 1. So typically what people ask at this point, oh, can you do all of this also with deep networks? Yes, you can, right? You just take a deep network with a softmax output. That's a policy. That's a stochastic policy. And everything what I've done here, you can just as well also do with any deep network, right? Or any other differentiable model that outputs a probability distribution. So you can also do then images and things like that with that. So, all right. So this was all bandit learning, right? It was all about picking that one action and then observing its reward. But we've already talked about some of the kind of problems where it's not just one action, but it's like a combinatorial object that we want to predict, like the ranking. That's the simplest version of this. So let me spend the last 10 minutes in taking everything that we've learned so far, not everything, but actually showing, oh yeah, you can do that for rankings as well. And rankings decompose in interesting ways that it doesn't become too hard. Okay, so what does the data for rankings look like? You have log data that looks like that. This was the ranking that was presented by our login policy null. That's our action that we took. And then we observe clicks on this ranking. But of course, the clicks, where we put them, the ranking influences where we get clicks, right? Whatever is high up in the ranking gets more clicks. So that introduces a bias again, right? And now what we want is we want to use this biased data to nevertheless learn a new ranking policy that does better than the ranker that collected the data. Okay, so why is this hard and how can we overcome that problem? So let's say we just have the very simplest learning problem. We have two ranking functions, A and B, or pi null and pi, and you just want to decide which one is better. So that's, hypothesis space of 2. And they rank the same objects, but in different order. So normally what we have is somebody like goes through it and manually labels all of the things as relevant or not, right? But that's very nice. So if we have this nice data, what's typically assumed in information retrieval, we can just define a metric, whatever metric we want, and then we can decide which one is better. So for example, the metric that I have here is the average rank of the relevant documents. So on the left, the average rank of the relevant ones is 3 plus 6 plus 7 divided by 3. That's something like 4-ish something, right? And on the right, we have 1 plus 2 plus 4 divided by 3. It's something 2-ish something. So the ranking on the right is better according to this metric. Very straightforward. But that's not the data that we have. The data that we have in our logs looks like that. You get a click on position 3. What we can maybe now deduce is that A and B were not relevant because the user kind of went over it and didn't click on them, right? We can probably also deduce that 3 was relevant. That's good. But how is that going to help us now in evaluating that other ranking here? So if we're just saying, oh, let's just assume that all the non-clicked results are not relevant, then we would come to the wrong conclusion, right? We would conclude that this ranking is worse than that ranking, which it's not, right? According to our ground truth metric. And for these yellow ones, we just really don't know, right? We just do not, we have missing information again. We just don't know whether they're relevant or not. And that's not that different from what we had before, right? There we also had actions where we just didn't know whether they were good or bad. Now, what can we do here? Deterministically deciding whether this ranking is better than that ranking, that just doesn't work, right? But that's not what we really want. We just want to know it in expectation. And so to get to that, let's think about a simple model of what user behavior could actually be in rankings. So let's say our metric is the rank, the average rank, or the sum of the ranks of the relevant documents. So, and that's something we want to minimize. And then we make some behavioral assumptions about our users. And one assumption that we make is if somebody clicks on something, then it's relevant and the user must have seen it, right? So there's this additional kind of random variable that comes in, this O of document, that indicates whether the user actually saw a particular document on the page, right? And clearly it's more likely that user sees something at the top of the page than at the bottom of the page. And so it's okay, you know, if something's clicked, it was seen and it was relevant. If something's relevant and seen, then it's probably also clicked. So that's not an issue, right? That seems reasonable. The problem comes if something is not clicked, right? And that can have two causes. One cause is users didn't find it relevant. The other cause, and that's what we want to kind of get at, the other cause is user didn't see it. And we need to tease these two causes apart. And it turns out that we can use the same techniques that we had in the first half. There's kind of and what we then do is every time now actually estimate, you get an unbiased estimator, an expectation you're doing the right thing. That means this thing here is an unbiased estimator of our target metric, and we can use it for learning. So we take that estimator, it's unbiased, we plug it into an empirical risk minimization objective, and ideally we also add the variance regularization, and we do this with SNPs. SNPs is actually tricky here, that doesn't quite work. And then we optimize it. So there's two questions now. Can we optimize this, solve this argument? And the second one is, how do we actually model these propensities, right? These probabilities that the user sees something. Well, the first one is actually, you know, how do we solve this optimization problem? It turns out that it's actually really easy. So I've shown it for ranking SVM. If you've seen a ranking SVM, you will say like, well, that looks exactly like a ranking SVM. And then you're like, oh, no, wait, there's a 1/Q in there. And that's the only difference, right? So the only difference is a little bit of a weighting. Otherwise, it's exactly the same theory also goes through. Ah, my mom's calling. The second, but you can do the same thing also for various other machine learning methods. It's typically very straightforward to actually extend them this way, or learning to rank methods. Then the second part is, how do we define this propensity model, right? So in the simplest case, you would just have one probability for each position, one propensity for each position. And that we can just estimate. There are little tricks that you can do. You can do like interventions, little swaps that you put in there. And you don't actually have to strap anybody into an eye tracker to see where they look. Through these little swaps, you can actually remotely estimate these probabilities, Q, of how likely somebody is going to look at a particular position. So here's the typical behavior that you get. So this is the number of training examples here. And up there, that black line, that's the logging policy that collected the clicks. And down on the bottom here, that's a supervised learning base. That's like, for our purposes here, it's as good as you can get. That's a ranking SVM that actually has access to all the full information data, not just the clicks. Then if you naively, without that 1/Q weighting, without the IPS estimator, train a ranking SVM, you get that green curve, something that's biased, right? And bias does not go away with more data. You're just more accurately estimating the wrong thing. The red curve is if you actually do like this propensity ranking SVM with the 1/Q weighting. And it converges, if you just get enough click data, it actually converges to to the skyline performance. Again, if you have something unbiased, more data helps. So there's also there's a zoo of other learning methods, like list-wise LTR, and many of those you can also translate into this kind of propensity weighting scheme. But I'll skip that for the purpose of this talk. So with that, I actually want to wrap up. So I hope what came across was, that just the general problem of not evaluating predictions, but evaluating actions, and how you can do that in hindsight in this counterfactual way, based on data that you've already collected in the past. So it's always answering these questions of how well would I have done if I had used a different policy? And we've seen multiple estimators for doing that. The model-based ones, right? These regression imputation ones that are high bias and low variance, and the IPS weighting ones that are unbiased but have a larger variance. And then we've seen that we can take both and turn them into learning algorithms. And there's a really rich field of designing these learning algorithms. And as you can see, there's interesting new machine learning issues that come up in the process that I think are very interesting research problems. So if you want to go more into depth, especially in terms of the estimators, I recommend you can listen to part of that Rex's tutorial that goes into more depth there. There's also more material and also like notebooks, how you can actually hands-on do this as part of the KDD tutorial that you can go to. There's a tutorial that's really more about this unbiased learning to rank by Martin de Rijke and others. If you want to go into this ranking direction, that's another good tutorial to go into. And if you want to start kind of thinking about, okay, where, what is the research that's being done here? Again, a good starting point are the reveal workshops that we've organized for the last 4 years. There's an upcoming one at Rexus again, where kind of a lot of the kind of early work on this is coming out. All right, with that, thanks for your attention, and happy, you can come afterwards here to me and we can discuss any questions that you have. All right, thanks.